All right, so today I want to start circuits. That's what today is about. You'll know what a circuit is? Does anybody know what a circuit is?
So the internet are like circuits and batteries and etc.
Well, a circuit comprises of a piece of conductor, some component, and some energy source in a loop. So you'll see what I mean just now. Let's just say, so let me introduce you to the symbols, right? Before we do anything, I should probably introduce you to the symbols. This would save the most time. So can we see this? Does everybody see this? Yeah or no?
Yes, sir.
All right. So this actually represents a battery. So Kestrel, was saying like a remote or something as a battery, right?
Yeah.
The battery is what gives the electrical components power.
Okay.
And this is what it looks like. Is what it looks like. So the longer terminal is the positive terminal, and the shorter terminal is the negative terminal. And this indicates a battery in the circuit. Um, just some extra knowledge. I don't know if you guys know this. What kind of current does a battery supply? Alternating current or direct current? Does anybody know? Does
Direct.
anybody? Yeah, it does direct current, DC current. The direction of the current never changes. Of course, you all will learn about this just now. So just to make sure you all understand this, what is this, guys? What's this?
A battery.
And what type of current does a battery supply to a circuit?
Direct currents.
Direct.
Direct current. Now, what? Okay, what terminal is the longer terminal? Let's see what does that represent?
E positive.
And the shorter terminal represents the.
Negative.
Negative.
Okay, this is what they could do, right? If I were to switch around the terminals, um, are you gonna call this positive? Are you gonna call the shorter terminal? Remind me, what's the shorter terminal?
Negative and
Negative.
positive.
And the longer terminal is?
Positive.
Right, and these represent batteries. Now, while we're on the topic of batteries and DC current, I want to explain DC current and I want to explain current in general. A battery, as you know, it supplies what kind of current? Not Kestrel, Amira, Adel, Shina, Zachary. What type
A
of
DC current, sir.
right? Probably saying, sir, what do you mean by DC current, boy? Let me show you what I mean by that. DC current is current that never changes direction. So I'm talking about current that always flows in one direction. Did any of you all learn about current before or not?
No, sir.
No? Okay, well, I'll introduce you to it then. That's not a problem. So you have two types of when we're talking about the flow of current, you have two different types. You have the conventional flow of current, which is the one we typically use, right? So conventional flow of current. And do you all remember what current was when we was doing Q is equal to IT or not? Do you all remember what current was? Does anybody remember what current was?
I, sir.
All right, I want you to read the definition.
The rate at which electric charge flows past a point in a complete circuit.
Right, because remember, if we're using Q is equal to IT, I would just be equal to Q over T, so it's charge over time. So it's the amount of electrons passing through a point in a circuit at a given point in time. That's what it is. Do you all understand that in a circuit, electrons will flow? If you don't understand that, just tell me, that's fine. So, okay, in a circuit, when you power on a circuit, there's a flow of electrons. Do you all know how batteries work on that?
So, oh, never mind.
Okay, so when a battery is fully used up, all the electrons are used up. You can think of it like that. When you hook up a battery to the charger, electrons flow into the battery and the battery gets charged. Remember, charge is just the amount of electrons you have in an energy storing device. So when we're talking about current, you can really think of it as the flow of electrons. Well, the amount of electrons flowing through the circuit at a point in time. So let me show you the conventional flow of current. So I'm going to draw a battery here. What terminal is that? What did I just draw there? What terminal is that? Anybody want to tell me?
Positive.
How what?
Positive.
This is a positive. What kind of terminal is this?
Negative.
Negative.
Right. I don't think you all would know what this is. Wait. Does anybody know what that rectangle represents in the circuit? Just curious.
That's a resistor.
Yeah, that's a resistor. And a resistor impedes the flow of current. Does anybody know what this is?
Say that's the LED.
Nah, that's not
Oh,
LED. That is a bulb, a filament bulb. A LED would look like this.
that's it.
So in the conventional flow of current, we are saying the electron flow is better, but we just always use the conventional flow of current. It was just decided by scientists a long time ago. So when we're doing this, we're saying that the current flows from positive to, you can take a guess. The current flows from positive to positive.
Negative.
So this is an example of a circuit. Notice that you have an energy device, which is a battery, and you have a closed loop. So if you have a closed loop, then the current has to go around and it has to pass through every single component to go back to the battery. So, Kestrel, and just seeing the current flowing through each component, like let me know if you're seeing that.
Yeah.
The current flowing through each component is going to, and there's obviously there's going to have some voltage drop across each component. So therefore, the battery is going to supply power to every single component as current is passing through each component. So you see how the current is passing through the bulb?
Yeah.
If enough current is passing through the bulb, what would happen to the bulb? What would it do?
That's no.
It would light up. I
Okay.
remember that. I remember that song, Light Up Sketches.
No.
No?
Yes.
Yeah, so everybody, do you all understand that this is a circuit? Like a circuit comprises of a power source and some components in a loop such that the current will pass through each component. If you do understand, let me know, Adele, do you understand this? Like a circuit comprises of like a power source, like a battery or direct or AC current, like from the wall socket, and components in a circuit connected in one loop with no gaps.
Yes, yeah.
I have a question. If I were to, I don't know, cut the wire over here, do you think the bulb will still light?
No.
No.
No, because how will the current jump this gap? It can't. So that will actually be something called an open circuit. But anyways, this is the conventional flow of current. So in the conventional flow of current, we say that current always goes from the positive terminal to the
Negative terminal.
Negative.
right. This one comes less frequently, but should still note electron flow of current. Alright, think about this. If conventional flow of current is in that direction, how you think the electron flow of current would be?
From the negative to the positive.
Yeah, that's it. And this is the electron flow of current. In the electron flow of current, it goes from negative to positive. But the one that we are going to use every single time is the conventional flow of current, unless they say something explicitly warranting the use of electron flow of current. So does everybody know what a battery is now? Yeah or no?
Yes, sir.
People?
Yes, sir.
Okay, and again, we'll always be looking at the conventional flow of current. So that tells us that current goes from where to where?
Positive to negative.
Negative.
Right, positive to negative. Cool. Let me ask you a question. When you put the battery in your remote, you just take it out, or you just leave it in the remote.
Leave it in.
Do you ever switch around the battery, or do you leave it the same way it is?
Leave it the same way.
Exactly. So if you leave the battery the same way it is, then the current is always gonna flow in one direction. Are you all seeing the current switch in direction?
No, sir.
Don't take my word for it, you know. If you don't understand, then tell me. Are you at any point in time, is the current switching direction like this? Or is it always going in one continuous direction?
So it
One
always goes in one
direction.
direction.
Exactly. So that's why we say a battery gives us DC current, because the current flows in one direction. Always. However, if you were to take the battery out and you were to switch around the battery, so this is now the positive terminal and this is now the negative terminal, what would happen to the flow of current?
It will change direction.
It would change direction. But are you taking out the battery of your remote and switching it?
No.
No,
No,
sir.
no, you're not. So battery is DC current. Like we just discussed, this component over here. What do you prefer? You prefer me drawing the components or just looking at this? Let me know.
Doing it.
Okay, all I had trauma from teachers that I just give all the notes and thing. Give all the handout.
Yes.
Yes, sir.
I understand. It's fair. It will take a little longer, but I'm not lazy. So what's the name of this component?
A resistor.
And I want a little bit give me energy, you know. I don't want this dead people thing like isn't always like Walking Dead. Or there's zombies, like give me some energy. Vanny, I see you join class. It's a good morning self. Vanny, what is this?
No, I saw you was talking to someone, so I didn't want to interrupt.
I see. You good, Vanny?
Yes, sir, good. How are you?
I did pretty well. And all I could put on the camera and thing, you know. Zachary. Put on the camera and thing. Yeah, Zachary. Zachary, ain't you put on the camera at a point in time before? But
I don't think so.
I don't think so. Do I even know what this look like? I feel like if I see Zachary in real life, I wouldn't know if it's Zachary.
I think you know how I does look. Yeah.
Like Kendrick Lamar.
Nah, nah, sir.
Then I don't know what it does look like. I see somebody on your status that look kind of look like Kendrick Lamar at time. Yeah. I don't know what it does look like. But look upon on the camera if all you want. It's fine. Another symbol for a resistor is this. Did you all ever see this before?
Yes, sir.
Right.
No.
No,
I
well,
shall know that.
now you know
Okay.
it. And a resistor, it resists the flow of current. So let me explain what I mean. Imagine you had a hose, right? And you connected to a pipe. If you have a hose and you connect it to a pipe, yeah, what will flow through the hose?
Water.
Water, right? And everybody understand? Guys,
Yes, sir.
Vanny, if you had a hose, like they would just say wash in a car, right? Vanny, does wash car sometimes or not?
Nah, sir, that's what my father to do.
So when you get your own car, you gotta consider that's for your husband to do.
Yeah, probably.
But in the time where you don't have a husband or you don't have a boyfriend or your father not there, what you gonna do?
I'll watch a YouTube video and hope for the best.
You go watch a YouTube. Nah, you kill me with that one. I'm not judging or anything, but actually, I cannot concern. How much of you guys will watch a YouTube video to wash a car? Basically,
Nah, sir.
Vanny, you just had to wing it, man. You just had to wing it like,
Yes, sir, I know to wash a car, just joking.
I was concerned. Yeah, but imagine you have a hose and you connect it to a pipe. The water flowing through the hose will be acting like the electrons, will be acting like the current. So the water flowing through the hose, we treat that as a current, right? If I put a kink in the hose, like let me just say a kink the hose over here, what gonna happen to the flow of water over here?
It'll stop.
It gets slower.
It gets slower. So that is what a resistor does on a circuit. I want you to think of the current as the water flowing through the hose. And when you kink the hose, what are you doing? Well, you're creating resistance. And that's what resistors do. It is kind of impede the flow of current. Do you all understand that?
Yes, sir.
So, is the same amount of current leaving the resistor, it's just that it's moving at a slower rate now. The flow of electrons is a bit slower. That's why that's what a resistor does. It slows down the flow of current. Let me make sure I understand that. Kestrel, do you understand what I'm saying? Like if you put a kink in a hose, what will happen to the flow of water at the
It's what
point?
stop.
Well, it wouldn't stop per se. It would flow, but it would struggle to flow through it.
Okay, yeah.
Yeah. And
Mm-hmm.
it will be the same amount of water though. Like it's the same amount of water. It's just like girl struggling to come out.
So you're just trying to say just slow down.
That's
Like,
all. That's all
yeah.
I'm trying to say. So the flow of water is impeded. That's the proper way to say it. So in a circuit, can you see the red arrow, guys?
Yes, sir.
Right. When when the current passes through the resistor, what will the resistor do to the current?
Slow
It's
it
what
down.
slow it down.
Exactly. It would resist the flow of current. Give me a second. Is there a more proper way to say this? Right. So I want you to think of the proper way to say this, right? So yes, a resistor does limit the amount of current flowing in a circuit, but it doesn't change the speed. That's actually a misconception. It doesn't change the speed. Or what it actually does is actually reduces the overall volume of electricity that is allowed to pass through. So, with the pipe, let me give you the example, the pipe again. Water is flowing through the pipe. If there's like a restriction, if there's a restriction in the pipe, let me just say somewhere over here. Um, what would that restrict?
The flow of water.
It would restrict the flow of water by reducing the what?
How much water? How
Yeah,
many amount
mom.
of it?
I'm looking for a word here, specific word. Starts with V.
Velocity or volume.
Volume.
Right.
Kesha, you know about Bernoulli's principle?
No.
Well, you should look at it like when you constrict a vessel like a tube or something and a fluid is passing through, you're gonna create areas where the velocity would change, the force would change, because it changed in the surface area going through. That's Bernoulli's principle. You can check it out. If you're gonna be an engineer or whatnot, you'll see it again. Are you gonna be an engineer?
No.
Well, I don't worry about it then. But the point is, by putting a restriction there in my circuit, I'm limiting the amount of water passing through there. So I'm decreasing the volume there. So that's what the resistor is doing in a circuit. It's like restricting the flow of current by decreasing the volume it has to pass through. That's what it actually does. But anyway, this is a resistor. And what does it do? It resists the flow of current. And we measure resistance in what? Does anybody know?
Ohms, I think.
Yeah. Resistance is measured in ohms, and the symbol for ohms is a symbol over here. Alright, cool. Another symbol that you have to be familiar with is a switch. Have you ever seen a symbol before? Zachary, have you seen it before?
Yes, sir.
Yeah.
So there's an open switch and it have a closed switch.
Yeah. And a switch, all it does, it creates a gap. Don't want to say temporary. Creates a gap in a circuit. Alright, a switch creates a gap in a circuit, and of course, it could close the gap. And if you close the gap, you would create a closed circuit. So I'd actually refer to this as an open circuit. And if the switch is closed, what would I refer to the circuit?
Closed circuit.
Closed circuit.
And in which one would current be able to pass through each component?
The open one.
Open circuit.
Right. Cool. The next one I want to look at that has come all the time. You need to know what. Should I do that when we're doing resistors? Do you all know what a variable resistor is? Also
No.
called.
The one where you can control your resistance.
Yep. And it's typically called a rheostat. Right, so let me show you what that looks like. So you typically see it looking like this. Have you all ever seen this before?
No, sir.
All right, question. If I'm telling you it's a variable resistor, what do you think you could do? Think. When I say variable, what I mean? Guys, okay. Let me go a little simpler then. What does vary mean?
Options.
Okay, so if I have a variable resistor, then I have what? Okay, let me try it. I don't want to tell you guys the answer. I wouldn't be helping you much if I did. I want you all to use your brain. In a resistor, it has a fixed resistance. I cannot. If I tell you 680 ohms, I can't change that. What do you think a variable resistor is then?
You could change the resistance, so you could like decrease it or increase it.
Right. That is it. Guys, it's any word. Variable. Think in maths. If something is a variable, what can we do? Like think of a function. Think of a function f of x is equal to 7x plus 3. What could I do with x?
You
X is a
could change the number
Exactly.
Yeah.
I could change the number, right? If I wanted, I could have say this is 2. If I wanted, I could have say this is 5. So you understand? A variable means that's something we could change. So in our variable resistor, we could do what with the resistance?
Change the resistance.
So we're changing about the resistance.
I am okay, so I want you to think of a hose, right? The more you kink the hose, what happens to the flow of water?
It would be a lesser amount.
It would restrict the flow of water even more if you kink it more, right?
Mm-hmm.
So I want you to think of a rheostat as like the same thing, like the more you kink the hose, the more it will restrict the flow of water. The less you kink the hose, the more it'll let water flow through. A rheostat kind of does the same thing but electrically. So let me show you. Let me see if I could show you the inside of a rheostat. Let's see if I can show you that. Let me show you. So this is what a rheostat actually looks like. 1 second. Uh, so this is a rheostat, and let me show you what it actually looks like. It's the actual rheostat. While we're on this topic, let me show you what resistors does look like. You all know what a resistor does look like? And read
No.
it. This is so sad. It doesn't show you these things in school. This is what a resistor does look like. So you have different types of resistors, right? Can you guys see that there are different color bands for the resistors?
Yes, sir.
Yeah, so like different resistors are gonna have different resistances. So they would resist the flow of current either less or more, right? And there's actually like a color code you need to learn that you'd be able to read off resistors. As a big electrical engineer, I should know, but what does it just do? I just take a multimeter and measure it. I don't really remember anything. All right, I read your stats. So here what happening, right? Catch right there.
Yes, sir.
This is a variable resistor. So can you see that we have current flowing through the wire? You see that, right? The current is flowing through the wire, and eventually it comes out through this end.
Yeah.
It's not dying, right?
Because of the cord at the bottom that going
Don't
towards it, see?
worry about this. Don't worry about this. If you want to vary the resistance, you wouldn't use C. You would use B. If you use C, you'll just get the same current that you entered in. Let me explain this,
Oh,
right? You
okay.
see this? You see this wiper thing over here? See this?
Yeah.
You can see it over here, right?
Yeah.
You can see how much the wire is wounded, like it real wind up, right?
Mm-hmm.
The more you wind the wire, think of a hose again and water flowing through the hose. The more you wind the hose around like a circle, what are you doing effectively to the flow of water?
Yeah.
Imagine I had a hose, right? And I keep turning the hose around. What am I doing to the flow of water?
You kind of preventing it from flowing in
Because
a certain
the water had
amount.
to go through so much loops,
Yeah.
so much loops. Right. So what I'm trying to say is, the further along you go here, the flow of current is what?
Um, Shorter.
The flow
lesser.
is restricted. Restricted.
Okay.
Restricted. Use our word. Use either you use impeded or restricted.
Okay.
Right. So you understand that the further along the coil of wire you go, it's gonna impede or resist the flow of current more. Think about the
Yes.
example with the hose again. If you keep wrapping a hose around in circles, you think what would that do to the flow of water?
It will restrict it.
Exactly. So here what? They came up with this idea. If we have a wiper here, I could actually slide this wiper. And when I slide this wiper, it's gonna make contact with the wire on top. So here what I was saying. If I put the wiper over here and it makes contact with this wire, do you think at that point, a lot of current is being resisted?
No.
No. So the resistance is gonna be like near like zero, right? If I put the
Mm-hmm.
wiper over here though, well the current had to go
Oh yeah. Okay.
and then it would be able to come through. So the
Mm-hmm.
resistance over there is actually gonna be a lot more. So by sliding this wiper along the coil of wire, we're creating a variable resistor. Depending on where I put the wiper, I'm gonna get different resistances. You understand?
So what's the point of the wiper if you just want current to go out? Unless
Well, you want to okay. The purpose of a variable resistor is to get different readings for current and voltage. That's the purpose of the ammeter. I'm not saying that's the purpose of the variable resistor. So you could plot a graph of voltage versus resistance, voltage versus current, whatever you want.
okay.
That's the main reason. And you was asking me what's the purpose of the wiper?
Mm-hmm.
Well, the purpose of the okay, again, you want to create a variable resistor. Variable means that the resistance it could change. That's what it is.
Okay.
If the wiper was in one fixed position,
You wouldn't get any variables.
now I wouldn't be able to change it. I wouldn't be able to change the resistance.
Okay.
However, if I could, you see this wiper over here, you could actually move it. You could slide it along this rod. If I put the wiper over here and it makes contact with this wire over here, it's gonna have a very low resistance.
Mm-hmm.
If I take the wiper and I slide it along to the end here, right? We think will happen.
You will get a large amount of currents
No, very large amount of resistance
resistance. Okay.
because it'll restrict the flow of current. If you just imagine the current had to flow through all this loop, and then come out. It'll restrict the flow of
Okay.
current. It's the exact same example with the hose. Like the more you twist up the hose and thing, it restricts the flow of water. It's the same thing over here. So question guys, let me make sure you understand this. Let me just say I have current coming in here and I have current leaving here, right? If I take the wiper and I put it over here, will I measure a large resistance value or a small resistance? If I put the wiper over here,
Small.
okay? Amira, if I take the wiper and I put it all the way to the end here, what kind of resistance I'll get?
A large resistance.
Right, because the current had to go whoa.
So all through the whole thing.
Exactly, and that kind of resisting the flow of current, you know. So I hope you understand this is a variable resistor. You also have potentiometers, which is also an example of a variable resistor, but this is the one we look at typically in CSEC physics. By the way, guys, until you know how another radio and thing. I don't know if all you have radio and thing or they young. All you know is a radio.
Yes, sir.
Okay, I'm just making sure. And you all know how we have like a button, like well not a button, but like a volume control. You know what I'm talking about?
Yeah, like the thing I had it turn and it had different dials on it.
What if I told you that was a variable resistor? It is. It is a variable resistor. I'll we'll see like a little experiment first.
Yeah.
Yes, sir.
Massive. I will show you something real. I will show you guys also what's a multimeter. Have you all ever seen a multimeter before?
No,
No,
sir.
No,
sir.
sir.
Wait, well, let me see notes. So as the name suggests, a multimeter could measure. Okay, when you hear the word multi, what do you think about multi? Multi.
Multiple.
Right. So it can measure multiple parameters. It can measure voltage, it can measure current, it can measure resistance, all kind of thing. So I'll show you guys something really cool. Give me a second, I'm just setting up. I'm looking for a variable resistor. I should have. Yeah, I just have these components lying around in my room. Okay. Um, let me stop sharing the screen and I'll show you this experiment. One moment. I could record it and thing. So I could actually see how this work. All right. I'm gonna spotlight myself. Okay, cool. Are you all seeing this?
Yes,
Yes,
sir.
sir.
All right. This is what you call this? Tell me the name on this. What is this?
With is a star.
Resistor, right? This is a variable resistor or a fixed resistor?
Fixed.
Fixed. So let me show you. This is a multimeter, right? It can measure voltage, resistance, current, all the cool stuff. Right. So and these are probes. So I want you all to tell me what is the resistance for this. Read the multimeter and tell me the resistance. Well, it's not supposed to be changing, eh? But this is a very, very accurate multimeter. So right, what is it?
Mm.
9.963.
Kilo ohms, right? Kilo ohms. Kilo ohms. You see any little K ohms? How many of you see any kilo ohms here? Well, it's no mega, but like
Yeah, where was the
right. So 9.97. It's rated for 10 kilo ohms. And so let's see, like it's about 10 kilo ohms.
Yes, sir.
Okay, and is the resistance really changing?
No, sir.
no.
No, right? Isn't this what you all are familiar with? Like, if you say want to increase or decrease the volume, like you turn it.
Yeah.
Right. So
Yes, sir.
let me explain how this working. Right. You have like a coil. I wouldn't say a coil. You have like a wiper. You have a wiper here. So like when you actually turn this knob over here, it's not really a knob, but let me just say turning this right. It's a wiper, and it turns when you turn this, and you have like how to describe this way? It's like this circle over here. This circle. And along the circle there's different levels of resistance. So by you turning this, you're gonna get varying levels of resistance. So let me stop talking and I'll show you what I mean. One moment. Right, so right now I connected it, right? Right, so right now this is like the lowest setting, right? What's the resistance? About what? You could just somehow like approximate. Was the resistance?
The 1.6.
All right,
Something.
I'm going to turn this now, right? I want to turn this. What do you think supposed to happen to the resistance?
It will get lower.
Nah, this is at the lowest setting right now.
Oh,
But
okay.
the resistance would increase.
I turn it a little bit. What happened to the resistance?
It's increase.
Can I turn it again? Oh, okay. Do you all understand why I call it a variable resistor?
Yes,
Because I could do what with the resistance?
change the value.
Exactly, I could change the value. And when I turn it all the way, the resistances, read out for me.
4.2, 4.42
What?
kilo ohms.
Kill
Right. I hope we actually understand the thing now. And not just like, seeing it like writing it on paper. But you actually understand it. Cool. So anytime you see the word variable, that means it could what? What does variable mean?
Change resistance.
Change your resistance, right. A variable just means change. Cool. What's another component we should look at? Well, you need to be familiar with a diode. Do you all know what a diode is?
That's
Okay. And we typically call it a semiconductor diode. When you hear the word semi, what do you think of?
Part of.
partially.
Think of a circle. When you hear the word semi, when you hear like
Yeah.
circle, what does semicircle mean?
Part
Half of
Half of a circle, right? So, and when you hear the word conduct, you think of something conducting what?
Electricity.
energy.
Right. So a semiconductor diode conducts kind of like halfway. If that makes sense. So let me explain. For a semiconductor diode, you have something called a forward bias and a reverse bias. So let's just say that current was flowing in this direction. Here how I want you to think about this. Doesn't it kind of look like an arrow? Low key? Doesn't it look like an arrow?
So it's like a play button.
Yeah, it does. But if you look at this by itself, what are it looking like?
Arrows.
I want you to think of that as the direction of current. Okay, think of that as the direction of current it permits. So it permits the flow of current in that direction. So if I have current flowing in this direction, it'll allow the current to flow through, it'll conduct. But again, it has semi in it, semiconductor. Semi. What does semi mean? Semi.
Half.
Half. So if it conducts that way, do you think it'll conduct the other way?
No, sir.
No. Check this out. Do you think the current will be able to pass through that barrier there?
Nah, sir.
Now I want you to think of this as like a wall, and it blocks the flow of current. So a semiconductor diode only allows the flow of current in one direction. Do you all understand that?
Yes, sir.
I only hear Zachary, no, Zachary's the only man in class. I don't know why I'm not hearing anybody else. Are they alive?
Yes, sir.
Are they sure? Are they kind of worrying me, you know? I don't know what the vibes are today. Everybody real quiet and thing. Why are they so quiet? Vani, how come you're so quiet? You alright?
Yes, it's just my throat feeling a little off. So.
Ah, okay. Well, I hope your throat gets better. Shane, are you alive? I know Shane had somebody data giving trouble.
Yes, sir.
So you see these components here on the circuit? Are you seeing this?
Yes, sir.
Yeah, this is a diode. That's what it actually look like. That's a diode in real life. Zachary, did you do rectification as yet?
So
Nah. Okay. All right. So let me show you what I'm gonna do the IV characteristics one time. So looking for a simplified one. Right, copy image. Right, so let me explain something. In this configuration is current passing through diode.
yes, sir.
Yes, sir.
Right, so we refer to that as forward bias. This is forward bias. In the other configuration is current flowing through diode.
No, sir.
No, so we refer to that as okay. If you want,
Backward.
I wouldn't say backward. I wouldn't say backward bias. I would say reverse bias. And a semiconductor diode, I'll try to give my definition. Just from what you see, try to describe what you're seeing.
So it allows current to pass in one direction.
Right. Cool, that's a semiconductor diode. The IV characteristic graph, it looks like this. This is what you all have to remember. You all have to remember this, like, this is the graph you all have to remember. Even simpler, at this level, like, I'll just have to learn this. Let me just draw the graph, like the simplest graph possible. When the voltage is quote unquote negative, do you think it'll conduct?
No, sir.
I want you to think of this as negative voltage minus V, and I want you to think of this as positive V. Guys, is it conducting when the voltage is negative?
No, sir.
No.
No. So if it's not conducting, guys, what will the current be? If it's not conducting when the voltage is negative, the current passing through the semiconductor diode will be what?
Negative.
Live.
No, think. If it doesn't allow current to flow through it, then where's the current passing through it then?
Positive.
Wait, think about it, guys. Is any current getting to pass through this?
No, sir.
Okay, so it's in the word. No current is passing through it. What would that value be? What would represent no current?
0.
0.
Right. So and in this, remember, this is V. This whole axis here is V, right? V would be positive here, and what would V be over here?
Negative.
Right. And when the voltage is negative, that's showing reverse bias. Is any current flowing through?
No, sir.
You'll have some small current flowing through. That's called leakage current. But we'll just put that for now. In an ideal world, it's supposed to be here, but realistically, it's be something like over here, right? And in the positive voltage, all it starts to do,
Current will increase.
yeah, it will allow current to flow now, right, guys? When the voltage is positive, what does the diode allow?
Current to flow through.
Exactly, you're seeing that or no?
Yes, sir.
Are you all sure you're seeing that?
Yes, sir.
Okay, cool. And so for this region, the graph will look a little something like this. Ideal one, it's supposed to be looking like this. So it's come on a second. Yeah, so that's what the IV characteristics will look like. Obviously, when the voltage is zero, it's not going to start to conduct immediately. And so there's something called the forward bias voltage. Different diodes have different forward bias voltages. Let me tell you guys. All right, so for silicon diodes, the threshold voltage, the voltage at which it starts to conduct, is 0.7 volts. I think for germanium, it's supposed to be like 0.5. But if you guys didn't know, you typically make diodes with two types of material, silicon or germanium. You learn this if you ever decide to do electrical engineering. But this is what the IV characteristics look like. Let me see if you guys understand this. So Kestrel, over here the voltage is what? What's the voltage over here?
0,
The voltage
1.
is zero. The voltage is
Okay.
zero, right? So will it conduct any current?
No.
No, so that's why you're seeing it like close to zero, right? Some current will leak through. That we can help that. Right? But when we start to increase the voltage and the voltage is now positive, once it passes the threshold voltage, it will start to what?
Flow.
Right. Conduct. Flow. Cool. You understand why we say semiconductor? Because it only conducts when the voltage is quote unquote positive. When the voltage is negative, does it conduct?
No.
No. That's why we call it a semiconductor diode. Semiconductor. Alright, cool, let's move on. What other essential ones you guys need to know, boy? Well, you need to know is an ammeter and while we're on the topic of diodes, I will look at light emitting diode one time, shall we? LED. Could anybody tell me what LED stands for?
Light emitting diode.
Wow. Alright, yeah, this is a light emitting diode. Amira, what do you think a light emitting diode does?
I don't know, it has produced light.
That is it. That's all. That is all. You know, it's like like them like the light strips.
The LED strips.
Yeah, we think it having that.
I guess
LED.
it's in diode.
Yeah, that's what it having it. Light emitting diodes. So, as the name suggests, it have the word diode in it and it have light emitting. So this is just a combination. This is a special type of diode. You'll see what I mean. So it's going to be the exact same symbol. The only thing that's going to change now is now it's going to actually produce light. So let me show you what I mean. So you put back the same diode symbol, and of course, you put this little symbol over here to indicate that it emits light. And that's a light emitting diode symbol. Do you think our LED will come on regardless of how you connect it? Yeah or no? Do you think our LED will come on anyway how you connect the battery? Or you have to connect it in a specific manner?
I
Connect
think
it
it
to
will
the
come on
specific.
anyway.
No. So Amira, again, this is a diode, you know. Does a diode allow the flow of current in both directions?
Oh, no, sir.
No. So the diode is the same property. It will only come on when I put the diode in this configuration. If you take the diode and you supply current in the other direction, it will not come on. Watch. So over here it'll be on, but if you try to put current in the other direction, will the current be able to pass through?
No, sir.
No. So will the LED shine?
No, sir.
So this is just a diode that emits light as well.
So that's where they get like the LED. Oh, so I don't understand like LED lights, lights within diode. So that's where they get it from.
Yeah, that's where they get it from.
All right.
Yeah. So now you know. Now you know. Now you know what LED means. light emitting diode. So guys, diodes only allow the flow of current in
One direction.
yes, one direction. But they know about one direction, or they're too young to know about that.
Yes, sir.
I guess and everybody else too young to know about that.
I know about One Direction.
We'll take a picture of this. Let's just peek. Yeah, boy. All right, cool. I move on. So that's a light emitting diode. What else I need to know about, boy? Well, you need to know it's an ammeter and a voltmeter. What do you think an ammeter does? If you had to guess.
And that is measure voltage.
Nah. It kind of sound like amps.
So
What
it
is
is measure current.
yes. Measures current. Now, a ammeter, it looks like this. Not an egg. I want a circle. Now, there's some rules when using an ammeter. If you want to measure current, wait, guys, you'll know about series and parallel connections? Or not? Adil, Amira, Zachary, Vani, Kestrel, Shina, do you know about series and parallel connections?
So I hear about it before, but I don't really remember.
Okay. Well, let me take a little detour to explain this then.
Let's say and series had two circuits, parallel only have one.
Nah. In a series circuit, the current never splits. So let me show you an example of a series circuit now. A battery here. So you have a resistor here. Let me just say you have a. Will you tell me what this is? Wait, what's the name of this? Anybody want to tell me? What's the name of this?
You see.
I was hoping a mirror would I tell me.
Wait the next time to ask me anything else.
All right. So in this circuit, how is the current going to flow again? Remind me. How does conventional current work again? How does conventional current flow?
From positive to negative.
Let me ask you that question. I think the LED go light here. Is it in the same direction?
Yeah.
Yeah, it will. Watch. If you ever confuse and ever forget it, watch. This is an arrow. Try to work the current had to be in the same direction. Alright, cool. At any point in time, did you see the current split? Or like is the current always flowing in series, like one after the other?
So it flowing.
Yeah, it's flowing, but is it splitting anywhere? Like is the current okay, you probably don't know what I mean by that. Let me show you what splitting means. Consider you had this circuit over here and the current was flowing like so. When the current reaches this junction over here, what happened?
So it will go two ways to like conduct the energy.
Yeah, it's gonna go two ways and it's gonna split in the middle. And when it splits in the middle, um, therefore that wouldn't be a series circuit because the current would split. But are you seeing any instances where the current splits over here?
No, sir.
No. So that's a series circuit. The current never splits. Please remember that. The current never splits. So if I wanted to measure the current in this circuit, I would actually hook up my ammeter in series. That's what I would do. And I think you could understand why. If I want to measure current, I would want the current to do what to the ammeter? Okay, think. I want to measure current. If I want to measure current, then I want the current to do what to the ammeter?
Pass through the amateur.
Yes. Yes. Thank you, Zachary. Guys, if I want to measure current, I would like the current to pass through the ammeter. That's why I have to hook up the ammeter in series. And again, if you're confused about series, series just means one after the other. The components are one after the other, and the current never splits. So the current is just flowing through each component here, and it never splits. So that's what I mean by a series connection. Let me show you a parallel connection real quick. When we move on to resistors, this will make sense. We'll do this in more detail. So I'm going to show you guys a parallel circuit now. If I find like this too complicated and thing and or like a real lost some, you know. Don't like stay quiet. Okay, so anybody want to tell me what this terminal represents?
The positive terminal.
And this terminal represents the.
Negative.
Okay, what's the name of this component?
Resistor.
So,
And what's the name of these components here?
LED.
electrolytes and diodes.
Right. So how is the current gonna flow in the circuit?
So you're gonna pass through the resistance lit at the point where the
Junction. Yeah, we're
you're
gonna
gonna
have
split.
Are y'all seeing what I mean when I say the current splits? Like guys, can you see it literally splitting in the middle here?
Yes, sir.
So if the current splits, wherever the current splits, that part of the circuit is in parallel. So what components are parallel to each other here?
The LED.
The LEDs. And will the LEDs light up?
Yeah.
Yes.
Yeah, because the current flows in the same direction as the forward bias, so it will light up. So in this circuit, we have well, the ammeter, the resistor, and the diode. They are in what? Anybody want to tell me they are in what?
Series.
Yeah. Guys, when you hear the word series, just think of one after the other. Until let's watch series and just watch episode after episode.
Yes.
Right. Adil, Amira, Zachary, Kestrel, Vani, Nico. I want to make sure everybody understand this for moving forward. So,
Yes, sir.
guys, okay, Adil, in this circuit, are you seeing the current splitting anywhere?
No.
And the current, see the little red arrows there, right? Tracing down the current. It never
Yeah.
splits. Now, if the current never splits and the same current is flowing through each component, you say that the components are in?
Yeah.
What would you say the currents are? The current, I mean, what was I saying? You would say that the components are in what? You tell me. The components are in what? Do you know?
No.
Alright, so I don't know, I have a feeling, I get a feeling sometimes I just be saying, yeah, you know. Like sometimes. That's true? If you're feeling confused or anything, it could tell me at any point in time, right? So Adil, what's the name of this component again? Remind me. Adil?
I've, I've figured out.
All right, that's our battery.
Uh-huh.
What's the name of this component? Adil, were you paying attention?
NASA.
Yeah, because I figured that out, you know. All right, so Adil, this is our battery. Do you know what we call this?
No.
Adil, how you if okay, it's all a rant, but I mean, if you come into class and you're not paying attention, you will literally learn nothing, right? Um, Zachary. Well, I know that Zachary and Amira was paying attention, and she will feel like you understand everything so far, or no?
Yes, sir.
But Adil, if you do pay attention, you will. This makes no sense, right? Um, so I can't help all if you're not paying attention. I literally can't. Adil, tell me now, what's the name of this?
Charger.
Nah, that's not a charger. Anybody wanna help Adil out? What's the name of this?
Battery.
It's a battery.
Right. Adil, this is a battery. The longer terminal is the positive terminal, and the shorter terminal is the negative terminal. So this is a battery. So Adil, what is this?
A battery.
Right, that's a battery. What is this? All right. So Adil, this is a light emitting diode. Light emitting diode. Say it for me.
A light emitting diode.
And what do you think a light emitting diode does?
It emits light.
Yeah, it emits light, right? Emits light. What do you think this is?
I do not know.
All right. Anybody want to tell Adil what this is?
A resistor.
A resistor.
Right. Adil, this is our resistor. And our resistor resists the flow of current. Think of current just like water flowing through a hose. Our resistor resists the flow of current. This is our resistor. Sometimes you go see me draw a rectangle instead. That's also a resistor. All right. So Adil, what's the name of this?
A resistor.
And this?
Are the same thing?
Same thing. Cool. Now in this, and do you know what this is?
No.
All right. So this is a. Anybody want to tell Adil what this is?
An ammeter.
Right. Adil, this is a ammeter, and it measures the flow of.
Current.
I wanted to hear from Adil. And so Adil, what is this? What is this? What's this?
Ammeter.
And it measures the flow of.
Current.
Good. And the little red arrows represents what?
The current.
Exactly, represents current. So the current. And do you know what type of current we call this? Electron flow or conventional?
Electron.
Nah, this is conventional flow of current. Conventional flow of current goes from positive to negative. Positive to negative. Let me ask you a question, Adele. Do you genuinely understand what I mean when I say split or no? When I say split.
No. No.
All right, think of a road, right? If I say the road splits at that point, what do I mean?
It turning.
Turning? Nah, I wouldn't say turning. Okay, when you hear the word split, what comes to mind? Split.
Like It went two ways.
Right, it goes two ways. So Adil, when you look at this circuit, is there two ways the current could travel or just like one way?
Well, it only have one way.
It only have one way, right? So the current will only travel along this route. Right, so another way to think about series and parallel, it's a series circuit if there's only one path for current to take. It's a parallel circuit if there's multiple paths for current to take. So in other words, Adil, I would say that the ammeter, the resistor, and the resist, remind me, what is this, Adil?
Like the LED
Right, I would say that all of these components are connected in.
and like the series.
Yes, that is it. All these components are connected in series because the same current flows through it. Good. Let's look at this circuit now. Again, what's the name of this?
A battery,
What's the name of this?
a resist. No, yeah, a resistor,
What's the name of this?
ammeter,
Nah.
maybe
The ammeter is the thing with the E. What's this?
oh, there's the LED,
Right. Would you say that this is a series circuit or a parallel circuit?
a parallel,
What components here are connected in parallel?
like the resistor and the LEDs,
Not the resistor.
the LEDs.
Yeah, the LEDs. Because when the current reaches this point over here, what happens?
It split.
It splits. So wherever the current splits, those components are connected in parallel. So the diodes are connected in parallel. I don't want to, when I have to explain every single thing all over again, it's kind of restrict the flow of learning. Now, I don't mind going over things, right? But I don't mind going over things when you don't understand. I don't want to have to go over things because you didn't pay attention. So I don't want to have this issue again. Right, Adil?
Yes,
Yeah. Right, cool. So long story short, when we measure in current using an ammeter, I must place the ammeter in what in the circuit. I place it into what here in the circuit. How am I placing the ammeter, guys?
In series.
Right. If I'm measuring current, I need to hook up the ammeter in series. Connected in series. So measuring current is important. What else should we be able to measure? Do any of y'all know?
Voltage.
Voltage.
Right. If our ammeter measures current, what do you think I'll call the device that measures voltage?
Voltmeter.
Yeah, voltmeter. And if our ammeter was a circle with a little A inside, what do you think a voltmeter will look like?
Yeah,
Look
circle
at the size.
E.
They're very creative, Ellie. Like they're very creative. And if our ammeter is connected in series, so I think a voltmeter would be connected.
in parallel.
Parallel.
Yeah. Probably wondering why, sir. All right. What's another word for voltage? Anybody can tell me? What's another word for voltage? I give you a hint. Potential.
Potential
And
difference.
it's
Nah, not potential energy. Potential
potential
difference.
difference. Okay.
Potential difference. Voltage is just like the difference in. All right, so like potential difference, you can think of it as like the difference in voltage across 2 points. That's what it is. Connected in parallel. So let me explain something. Let's just say I had this circuit here. Okay. What do you all want me to measure the voltage of? Give me a component in the circuit you want me to measure the voltage of.
The
Where
LED.
LED? Well, the proper way to say it, I would say the voltage across the LED. So the LED would have a voltage across it. The resistor would have a voltage across it, and well, for ammeter, there's no voltage across it. Our ammeter just measures current, right? So let me explain. Potential difference is the voltage across 2 points. So let me ask you a question. Do you think the voltage across this do you think the voltage at this point and this point is the same?
No, sir.
No, the voltage is not the same. So if I want to measure the voltage across the resistor, I will hook up my voltmeter like this because I want to measure the potential difference between these 2 points. Does this look like a series connection or a parallel connection? That's all you have to say.
Parallel.
Parallel.
Adele, do you know why I'm saying parallel?
Yes,
Why?
because it should go two ways.
Exactly, it will go two ways. When I reach this point, the current would split. And this brings up a good point. When you're learning about ammeters and voltmeters, you will learn that ammeters, ideally, it should have a resistance of 0. So, like, ideally, an ammeter should have a resistance of 0 ohms. In reality, though, it just ends up having a really low resistance. I'm killing so much birds with one stone right now is crazy. Yeah. So, and I should probably explain this. I'll explain that just now. Let me ask you that question, right? So, Adil, you just tell me it was a parallel circuit, which is true. Um, Adil, what is the only thing I want the voltmeter to measure?
Voltage.
Right, which is the difference across the component, right? Now, would I want the voltmeter to be taking away current from the circuit?
No.
Anybody else? Would I want that voltmeter to be leaching current from that would be flowing through the circuit? What is the only thing I want the voltmeter to measure? What's the only thing I want the voltmeter to measure?
The voltage.
So do I want current to pass through it?
Nah, sir.
No, sir.
No, so let me ask you that question. If I don't want any current to flow through the voltmeter, it should have a resistance or what?
Zero.
Think about that, you know. If something have a resistance of 0, what I mean?
It don't have any flowing through.
No. Okay, so resistance talks about, okay, the higher the value, the more you're going to restrict the flow of current. If it have a resistance of 0 ohms, it means that it's not restricting any current, like the current is going straight through. Okay, let me make sure we understand this. I have to understand the fundamentals. If the resistance is 0 ohms, it's a short circuit. Let me explain. If it is 0 ohms, is there any resistance to resist the flow of current?
No, sir.
So 0 ohms. Amira, if the resistance is 0, is there anything to resist the current?
No, sir.
It's in the word 0. If it have 0 ohms, is there anything resisting the flow of current?
No, sir.
If there's nothing resisting the flow of current, will current stop or will current easily flow through?
It will easily flow through.
Do I want current to flow through the voltmeter?
No, sir.
So what kind of resistance I should have?
A variable.
No.
So I give up.
Then don't give up. Or they could do this. Hear what I'm saying, right? If a circuit has a very low resistance, what will that mean about the current? What will that mean? What will that imply about the current? A circuit has a very low resistance. What does that mean about the current? I want to
The
let you think.
current would be high.
Well, I wouldn't say the current.
So it will
Um,
allow it to flow through.
well, Zachary not wrong. If a circuit has a very low resistance, a lot of current will flow through. Vani, Kestrel, Zachary, Adel, I want to make sure we're on the same page. Nico, if a circuit has a low resistance, is it restricting the flow of current?
No.
No.
No. So would you say 0 ohms is a low resistance or a high resistance?
Hello.
A low. So if something has a low resistance, will it allow current to flow through or will it block current?
Allow it to flow.
Allow. Amira, I want you to think. I want you to figure this out. I want you to use that brain you have. You can do it. So Amira, if something
Yes.
has a low resistance, what will it do to the current?
So it will allow a lot of current to flow through.
Allow current to flow. But in this scenario, what do I want? What do I want to do here?
So you want to permit current from flowing through the voltmeter.
I want other way to flow through, right?
Yeah.
So what kind of resistance I should have?
High
Ha.
resistance.
If we live in an ideal world, the resistance should be what?
High.
Well, it should be infinite. Should have
Alright.
an infinite resistance. If something has an infinite resistance, what does that mean?
So I don't know
The
that
current
example
could pass
of it.
through.
No current could pass through. None. None. So do you all understand that a low resistance would allow current to flow? If it's a very high resistance, what would I mean?
A little bit of current will pass through.
Right, that's the best we could do. So for the voltmeter, it needs to be hooked up in, what kind of connection is this?
Parallel to the resistor.
Right, so that's why a voltmeter measures voltage and is connected in parallel. So if I wanted to measure the voltage across the diode, how would I connect that? Anybody feel like they could draw it on the screen?
Yeah.
Draw it there. See if you all could draw it. How would I hook up the voltmeter to measure the voltage across the diode?
So you using the draw tool on the screen.
Yeah, you could use it.
Uh, so, so I use my laptop to draw, so it wouldn't be too.
I find that good. I find that real good. It looked like you draw a little flower here though. Yeah, it looked like you draw a little flower over here. Do you all think he's correct or he's wrong?
Alright.
Yeah, because I always hook up a voltmeter in what?
Parallel.
Parallel to the component. Are you surely understand that or no? If you don't understand this, they can be pressure, later on. Real pressure. See, I tell me no if you don't understand this. Do you or do you not feel bonita? Yeah. You know what I mean?
The to measure the voltage, you will have a infinite resistance. So, where the resistor would be exactly like it would be at the point where the like on the wire itself when it's like what is call it splitting.
Well, the voltmeter itself has like a internally high resistance. Like, let me see if I can show you.
So when the current passed through the voltmeter, it would resist it.
Yeah.
Uh,
Let me show you how it is actually work though. Again, if you do electrical engineering, you can learn about this. Come on a second. Yeah, so voltmeters have like a internally high resistance. So like, let me show you what I mean by that. And this type of a voltmeter I'm talking about is the analog one. Let me show you. I don't know if I'll ever see this in my life. I doubt I'll ever see this before. So like, exactly how it does work, right? You have like a calibrated galvanometer, right? So like, look at this, right? Like the current is gonna like obviously it's connected in parallel, right? You can see that, right? The current gonna flow through.
Yes, sir.
As you could see, by the galvanometer is what actually gonna deflect. That's a little needle you're seeing over here. Seeing that?
Yes, sir.
Inside the mechanism itself, it has a very high resistance in series with it. So like internally, you see this component here? That's the galvanometer. To that, it has a very high resistance connected to it in series.
Yes, sir.
Yeah. So like, watch. You see any component here? You're connecting this part over here in parallel to your circuit, and then this part over here has a very high resistance and is connected back to the circuit. Let's just put a resistor in the middle. Let me just say we want to measure the voltage across the resistor. This is what the voltmeter looks like on the inside. You have a, a, a galvanometer, and in series with the galvanometer, you have a very high resistance. Yeah. Right? So ideally, a voltmeter should be connected in parallel, and it should have a what type of resistance or mirror? A low resistance or a high resistance?
Right.
If it was even a perfect world, it ideally should have a resistance or what?
Infinite.
But realistically, we just end up using a what type of resistance?
A
Uh-huh.
very high resistor.
Yeah. In reality, okay, I feel like we could call that a day when it comes to components for now. You wouldn't really see any other type of components in the CSEC level. Wouldn't really see that. Let me just underline everything. Make it look a little bit aesthetic. I prefer this as opposed to like just making all the copy down thing. Yeah or nah?
Yes, sir, 100%.
Just switch. Right, so let me do some past paper questions now. I'm not really excited. So there we go. We'll do some multiple choice questions. Because these type of questions I like to bring it to multiple choice. 1 second. I sent you guys all the physics paper one solutions, right? Like the compilation. And also I believe I'll also send you guys 2026. I feel like a little utilize these resources, to like the full extent. How much of it is like actually look at the resources and use it?
Yes, sir.
Well, I'm not surprised that Zachary did. Zachary seemed like a upstanding student, responsible student. How much are you guys genuinely use your resources like the 17-hour notes or like the all the paper one solutions in detail? Like I just curious. Just Zachary? That's crazy. If you all want to be extraordinary, you have to do extraordinary things. Otherwise, you'll be average. And nobody wants to be average, but nobody wants to put in the work to be above average. You know what I mean? Okay. Okay, somebody other than Zachary, answer this question for me. Adil, read the question 45 for me.
A voltmeter has a very high resistance so that it can be placed in a parallel with a component and not affect the circuit. B series with a component and not affect the circuit. C parallel with a component and the voltmeter does not heat up. D series with a component and the voltmeter does not heat up.
Which one do you think is the answer? So we're talking about a voltmeter and it has a very high resistance. A, B, C, or D?
I think is B.
B? Now let me check back the notes. Check the voltmeter. Alright, so Adil, check that. Check it back there. 45. Which one do you think is the answer? Right, so wait, Adil. The voltmeter measures. What does the voltmeter measure?
Voltage.
And it must be connected in.
Parallel.
Right. And in it should have a what? Low resistance or high resistance?
A high resistance.
What's the answer? A, B, C, or D?
C
Nah.
is A.
Is it? Do you know why it's A though? Okay, let me
Because a voltmeter is in a parallel circuit, and yeah,
so it's in a parallel circuit. Or what happens at parallel circuits, Adil and Kestrel? What happens in a parallel circuit?
it
It'll
splits the
split.
Yeah, do I want the voltmeter taking up any current from the circuit?
no.
No. If I don't want the voltmeter to be taking up any current from the circuit, I want a what type of resistance?
High resistance.
I want a high resistance, so it will not do what to the circuit.
It will not affect it or take up any currents.
Yes, that is it. So, Adil, I put my voltmeter in parallel, and because I put it in parallel, current is prone to splitting. But I don't want the voltmeter to take any current at all. So I put a very high resistance for the voltmeter so very little current passes through, so it would not affect the circuit. I don't want the voltmeter or the ammeter affecting the circuit. So the answer is going to be A, because I would put it in parallel and it must have a high resistance so it doesn't affect the circuit. It wouldn't pull current from the circuit. So 45E. Remember that, right, Adil? So Adil, whenever you see voltmeters, they are placed in what? Series or parallel?
Parallel.
And they have a what type of resistance?
A high resistance.
High resistance. Good. Right? Okay. Right? And I want a high resistance so it wouldn't do what to the circuit?
So it wouldn't take any like charge
Nah, so it wouldn't take any current from the circuit.
current, yeah.
And so long story short, it must have a high resistance so that it wouldn't affect the circuit. So 45E. Anybody want to tell me what this would have looked like if it was a ammeter instead?
So, would that be B?
Yep, maybe. And they would have. See if you can tell me what the sentence would have been instead.
An ammeter has no resistance so that it can be placed in series with a component and affect the circuit.
Excellent. Which of the following circuit arrangements is best suited for accurately measuring the voltage across the lamp? So we want to measure what here? Who want to help me with this question? 46.
Me.
All right, so Kestrel, we want to measure the voltage what? The voltage.
Across the lamp.
So if I'm measuring voltage, I must connect the voltmeter in what?
Parallel to
Must
these
be
components.
parallel. You think 46 is correct? And 46 A.
No,
You want to tell me why it's wrong?
because it's in series with the circuit and in a parallel to anything.
Exactly. What is this? Let's see now,
Um,
right? Let's see now the voltmeter here is in series in the circuit. Like that not possible. That's not possible at all. How do I make any sense? It's a red flag. It's a red flag. B. Is B the correct?
it look like it could be correct.
I'll wait to read the question.
Or across the lamp. Okay, no, it's incorrect.
This will be measuring the voltage across the what?
Battery.
Yes. Cash, really impressive, my boy. Okay. Big up you. Big up you. So in this circuit, the voltmeter is actually measuring the voltage across the battery. That's what we're doing. Do we want that?
No,
Fanny, what do we want to measure?
The voltage across the lamp.
Correct. This is wrong because it's measuring the voltage across the battery. We don't want that. C. Tell me, Kestrel.
C is correct because it measures the voltage across the lamp.
Good. Right. Adil, what's the name of this component?
Ammeter.
Nah. Ammeter would be that. That would be ammeter. This is actually a bulb.
Uh,
This is the bulb. Yeah. That is the bulb. This is the what? Talk to me. What do you think that is?
the the voltage.
Nah, that's the voltmeter. That's the
The volt
voltmeter. And what is this?
the battery.
Good. You remember that. on this.
the diameter, the
You could do it, Adel. I believe in you. What's the name of this little squiggly line?
start with the aren't
It does start with a R.
resistor.
Yep. Ah, boy, big up yourself, Adel. That is a resistor. Now, see the answer. In the question, they wanted us to measure the voltage across the lamp. And well, this is the lamp, and we're measuring the voltage across it. That's the answer. Why is D wrong, Kestrel?
Because it not
What I doing? What I measuring?
the voltage across the resistor, but it extended with the lamp also, so that why I'm confused.
This will be wrong because this measures voltage across resistor and what?
The lamp.
Yeah. Which would actually be equal to this voltage, eh? I don't know that yet, but there's something called Kirchhoff's voltage law. And like, okay, if I supply in the circuit with this power, with our battery, right? The battery would have a certain voltage, a certain potential difference. Now, Kestrel, do you understand that there will be a voltage across the resistor and there will be a voltage across the lamp?
Yeah.
Well, if I am supplying a voltage across the whole circuit, then when I add up this voltage and this voltage, it's actually going to be equal to the voltage I supply. Yeah. So
Okay.
when we measure this, we actually measure any voltage for the battery. Yeah. And obviously this is wrong because we just want to measure the voltage across the. We just want to measure the voltage across the.
For the lamp.
Exactly. So this is wrong. So you did a really good job. Make up yourself. You guys would not know this one per se. I'll tell you the answer. The answer is 90 degrees. Yeah. Yeah, we didn't do the prerequisites to understand this. I believe Zachary would have do it. Zachary, recall that if you have a north pole and a south pole, you're gonna have the magnetic field lines going from north to south.
Yes, sir.
And if you have a current carrying conductor in the magnetic field and you move it, it'll generate a what?
Focus.
Now it could generate it would induce a current in the wire there, the red wire.
So I don't understand any other
No problem. I'll have to
things.
explain it to you then. Don't worry, when we reach there, when we cross that bridge.
Yes, sir. My teacher not that. You not that good, sir.
You know, I just be real scared of this be saying this about me. I just be real scared, like I just be so
Nah, sir.
because like all they just be talking about it just so casually is like I can imagine what they be saying about me.
No, so literally just now, me and Kesha was saying that we're gonna take our physics teacher in school salary and we're gonna get you it because
How will they gonna do
yeah.
this?
So I don't know.
But that would be nice though. I need money. I need money.
All right, we still will figure out how we.
Thank you, thank you. All right, what is the period of the current? So guys, we would have done waves already. I want to see if I remember waves. What is period? Anybody want to tell me? We did this already. What is
A
period?
complete oscillation. Wait.
Yes, a
Oh.
complete oscillation. What is the time for a complete oscillation?
4 seconds.
Yeah, 4 seconds. This is a complete oscillation. So the answer for 48 is B. Because watch. Start from 0, you went up, make a crest. Then you went down, make a trough, you come back here. There's a full oscillation. So Kestrel was right. 48p, 4 seconds. Gonna move on. Yeah, you wouldn't know this question, but I'll explain it. I'll give you a little insight into it. Again, we're real killing birds today, buddy. Damn. Let's look at connecting resistors in our circuit quickly, shall we? So again, what types of connections do we have? Anybody want to remind me? What types of connections do we have?
Series and parallel.
Yep, we have series and parallel. Which one do I want to look at first?
Series.
We already kind of have ideas of how this is work, right? We're not going into this blind because we went through series already. If it's a series circuit, then the components are, well, one after the other. And there's only what? Anybody want to complete my sentence? There's only one, what?
Flow. Flow.
I would say only one path for current to flow. Like, look at this circuit, right? Gonna call this R1 because this is a resistor and there's another resistor. If I were to draw the flow of current in the circuit, remember the longer terminal represents what Adil? What does the longer terminal represent?
Positive.
Positive. Yeah, positive. And the shorter terminal represents what?
Negative.
Negative, right. So we're gonna go from positive
To negative.
Negative.
like so. Now, when you look at how the current flowing in the circuit, does the current ever split? Imagine there's a road, right? Imagine you're in a car and you're driving. At any point in time when you're driving, is there any, and you're staying on the road, right? Is there any way where you're seeing like a junction, like a split?
No, sir.
No. So this is a series circuit. And a series circuit is very, 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 very easy. If you want to find the combined resistance, all I would have to do, I would just have to add the resistances. So I would say R1 plus R2. That's all. Real simple. Now, what are some characteristics of a series circuit?
Components come directly after each other.
Yeah. So in a series circuit, one path current to flow. There's only one path current could take. This brings me to something important. If one component fails, what happens to the circuit?
The circuit will fail.
Exactly. If one component fails, this creates an open circuit. Because, like I say, I'll hear what I'm saying, right? Kestrel, current could only take what? In a series circuit, right? How much paths are there for current to flow?
One.
Exactly. So if one of the components blows something or like it stopped working, what happen?
The whole circuit wouldn't be able to function or flow.
Exactly, because imagine I remove this resistor, right? What happened to the circuit now?
It would not flow.
Yeah, the current wouldn't be able to flow, right?
Yes.
You think you would use this kind of wiring to wire your house?
No.
Zachary, Amira, Adil, Vani, Nico. You think you would use this type of wiring to wire your house?
Now, so
No,
Imagine
sir.
Imagine your fridge stop working and your whole house stop working. You know what that's happen?
Nah, so
No. Imagine one of your
so
bulb, imagine one of your bulbs in your house blow and your whole power stop working in your house. Like everything just stop working. You know what that's happen?
nah, so
No, sir.
No, you know what that's happen, right? No siree. So in a series circuit, there's only one path for current to flow. If one component fails, it creates an open circuit. Come on a second. Let me see if I get a diagram. Yeah. Okay. See if I get a diagram. Surely we're talking about. So a misinterpretation students just make they just think like here what, right? Students just think that when current flow through a resistor, the current is changed. How much do they think that? How much of you guys think that when current flows through a resistor, the current changes? Be
it
honest.
even changes.
Wait, give me a second. I have been asked that question. It shows I'm more than likely you understand. Check this, right? In a series circuit, can you all see that the current is like one continuous current flowing through the circuit?
Yes, sir.
Are you seeing that, right? Yes or no? Guys, are you okay?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. In all of these diagrams that are showing you all, are presenting to you guys, the current flowing through each component is the what? Anybody want to tell me? Maybe I need a more obvious diagram. Give me a second. One second. Look at this, right? In every single diagram I have here, it is suggesting that the current going through each component is the okay. I think I'll see it. Kestrel. When you look at this, right? You're not seeing any numbers,
Mhm.
right? But it looks like what? What does it look like? That represents the current.
The colors.
Okay, this diagram probably not good enough. Let me move on to another diagram. And they put a
Okay.
number. So the current flowing through is what's the current?
Um, mm,
What's the current?
or 0.2 amperes.
Okay, maybe this diagram not good enough. Let me move on to another diagram. Check this diagram, right? How much current is leaving the battery? I mean, how much current is flowing out the battery?
Um, point. Another guess, 0.2.
No, like you gotta guess, like it's telling you right here. I is equal to
Okay.
0.2 amps. Right, check it out. You know, the positive to negative. You know the drill by now. Positive to negative. So let me ask you a question. 0.2 amps are current leaving the battery. Right? So your power ammeter here, it still measures the 0.2 amps. So let's see now the ammeter still measures 0.2 amps. How much current is the battery supplying? Tell me.
0.2 amps.
I'm not trying to trick all you, know, like it right in front of you, I promise. Amira, Kestrel,
So
Adip,
0.2
Vani.
amp.
Right. The current only have one path to take. So when the ammeter reads it, what's the current the ammeter tell you?
0.2.
Right? And the current do only have one path it could take, so it continues going through. So what is the current flowing through this resistor?
0.2.
Yeah, 0.2. I mean, like, guys, like, okay, think of the current as like a car driving on the road, right? In a series circuit, it only have one way the current could flow. It don't have any other way. So what current will flow through this resistor?
0.2.
Right? What current will flow through this resistor?
0.2.
Right. The point I'm trying to make is in a series circuit, read it from me.
Current flowing through each component is the same.
That is what I'm trying to say. That is what I'm trying to say. Check it out. Over here, you see that it's just one path the current could take. So the current flowing through this component, flowing through this component, flowing through this component is the same. Same thing over here, you see in the current flowing through each component is 0.2 amps. Yeah. You understand? I feel like
Yes.
I feel like I'll still understand it.
So we could do this
See.
another diagram.
No problem. So like look at this diagram here. Let me just say we have a current of 1 amp and a flowing. Anybody want to tell me what is the current at this point over here?
1 amps.
1 amps. What's the current here?
1 amps.
What's the current here?
1 amp.
What's the current here?
1 amps.
What's the current here?
1 amp.
What's the current here?
1 amps.
Right, because the current could only take one path. So in a series circuit, everywhere the current is the same. So the current through each component is the same for a series circuit. That's what I'm trying to say. Are you understand that?
Yes, sir.
Now something I was trying to explain to you all earlier. Check this, right? How much was the voltage across the battery?
9V.
9 volts, right? I want you to do something for me. I want you to add the voltage drop across the lamp. I want you to add the voltage drop across this lamp. And I want you to add the voltage drop across this lamp. And tell me what you get. And by the way, would you all say that this is a series circuit or a parallel circuit?
Series.
I would say it's a series, right? Because like the current only could take one path. I want you to add up 3, 4.8, and 1.2 from that. Tell me what you get.
9.
Are you seeing that 9 anyway? Where we get a 9 from?
Battery.
Battery.
Exactly. So what we're saying is the sum of voltage drops across the circuit. Like what? 3 volts is drop across this lamp, 4.8 volts is drop across this lamp, and 1.2 volts is drop across this lamp. But where you getting the voltage from?
The battery.
Right. So Kirchhoff's voltage law says that. Well, I like to remember that like a different kind of way. Kirchhoff's voltage law. It says that the sum of voltage drops in a circuit, well, I like to say is equal to the source voltage. So like again, 9 volts in the circuit supplied by the battery. So then the sum of the voltage drops must be equal to 9 volts. As always remembered. So when I add up the 3, the 4.8, the 1.2, I suppose I get 9. Because that's the total potential difference across the whole circuit. So by adding up each drop across each component, I'm supposed to get 9. Which you see we do. We do get 9. But long story short, in a series circuit, the current through each component is the... Anybody want to tell me? Guys.
Current is the same.
Right. Because the current only has... Figure it out. Or we could do this. The current is the same because it only have
The one route for the current to pass through.
yes, that is it. Thank you. Yeah. It only has one route for it to pass through, so the current will be the same everywhere. Cool. And you have a bunch of series circuits over here, so knock all yourself out. And if you want to combine resistors in a series circuit, all you have to do is just add them. Real straightforward. Very, very straightforward. So I feel like we could answer this question now. Amira, wait up, more this, give it a read.
Items 49 and 50 refer to the following diagram, which shows 4 different circuits labeled 1, 2, 3, and 4. In which of the circuits can the effective total resistance be calculated using the relationship RT equals R1 plus R2?
All right. So they're saying RT is equal to R1 plus R2. What kind of circuit does this suggest, guys? Anybody want to tell me? What kind of circuit is that?
Series.
Series.
Yeah, there's a series circuit. We just look at that. Just look at that. It's a series circuit. So if it's a series circuit, we're looking for what? What are we looking for if it's a
One part for
series?
the current to flow.
Say that again?
One part for the current to flow.
Correct. Let's look at this circuit. Of course, we're looking at conventional flow of current. The current will leave the positive and go to the what?
The negative.
Right. Oh, what happened in here?
It's
Have a split.
There's a series circuit?
no, sir.
A split.
Nah, something wrong there. That's not a series circuit. So is that my answer?
No,
No,
sir.
Nah, that's not correct. What about this circuit? Let me go. Tell me.
splitting.
Still wrong, because it's splitting.
About
Correct.
you sure?
Wrong.
Watch. When the current, okay, the current gonna leave the positive. It's gonna go here, but then what gonna happen?
So it just can't go like, all right, so never mind.
Okay, you're looking for any circuit that don't have a junction. Imagine you were driving a car, right? When you reach this junction over here, you can either take a what?
I left or right.
Exactly. When you reach this junction over here, what you could do?
Left or right.
You understand why we just call it junction?
Yes, sir.
You can either go here or here. Let me check this one out. Are you seeing anywhere any junctions?
No, sir.
No, so this represents our kind of circuit.
Series.
Series.
And if it's a series circuit, then the total resistance could be what?
R1 plus R2.
R1 plus R2. EP. So what's the answer for 49?
Four.
D, right?
Yes, sir.
Cool. 50. If R1 is equal to 60 ohms and R2 is equal to 40 ohms, then the effective resistance in a circuit labeled 2 is, so 2. What kind of circuit is 2?
Parallel.
Parallel.
Right, let me show you how to handle parallel circuits now. And like I told you guys, like, these classes would go on for more than 2 hours because we had to make up for the time we miss. Right?
Listen.
I didn't see Ollie in so long, so we had a, peace. And I see Ollie had 4. I go after we do question here after 50 or call a day. Because I feel like in the next class I want to move on to Ohm's law and thing. Alright. So are they okay with series circuits, right? If it's a series circuit, then the total resistance is just the sum, like R1 plus R2, that kind of thing. I'm gonna call
Yes,
it.
sir.
All right, let's move on to parallel circuits now. So in a parallel circuit, we know what we're looking for, right? So in a series circuit, there's one path for current to flow. What would I say for parallel?
It is have a split. So it have two different routes that the current could take to go.
Yeah, it could be multiple, eh? It could be multiple. It just have to be two.
Okay, so
So in a parallel circuit, there are multiple routes. Multiple routes. Yeah. And you would say current splits up at junctions. And that makes sense, right? Because if you're driving a car, anytime you reach a junction, what you have to do?
go left or right.
Exactly. Exactly. And let me just draw a parallel circuit for you all quickly. Oh, by the way, in a parallel circuit, voltage across each component is the, anybody wanna guess? I'll give you a hint. Your house is wired in parallel, and it is hook up everything to the wall. So think, the voltage across each component would have to be the what?
You see?
Exactly. Think about it. Would you want your fridge to get less voltage than your charger?
Nah, sir.
Amira, Kestrel, Adel, Vani, Nico, think about these things logically. And you just hook up your appliances to the wall?
Yes, sir.
Do you want your TV to be getting less voltage than your fridge, or you want that?
No, sir.
Nah, you want each appliance to be getting the same voltage. Right? All appliances are made for like a specific voltage. So your house is wired in parallel. Domestic applications, that's like how something is connected in parallel. So think of it like that. Voltage across each component, therefore, would have to be the what?
Him.
Is the same. Cool. So realize for parallel circuit, the voltage across each component is the same. But for a series circuit, what was the same? What was the same for a series circuit?
The current.
Current.
Yep. In a parallel circuit, if one component goes, do you think the whole circuit breaks?
No, sir.
No,
No,
sir.
sir.
I mean, like I just say, like your house is wired in parallel. If your bulb blow, do you want like your whole house to just have no power? Does not break. The answer is no. If one bulb in your house blow, you don't want your, think about that. That'll be real bad, right? Imagine one bulb in your house blow and all the power in the house gone. Think about that for a second. That's like them Christmas lights. You know what I'm talking about? Them Christmas lights.
Yes, sir.
Yes, sir.
Yeah, I think you understand it now, right? If one bulb blow in the Christmas lights, the whole thing goes, and that's because it's hooked up in,
Direct. No, heavy direct. I'm serious.
yeah, series. So it does not break if one component fails because there are what? In a series circuit, there's only one route or one path for current to flow. So if one component break, That is it. It can't take that part anymore. But in a parallel circuit, it doesn't fail because they are
multiple routes to take.
correct. Okay, so let me give you an example of a parallel circuit. Give you a couple examples. Which symbol are you prefer for the resistor? The squiggly line or the rectangle?
Quickly line.
And so,
Squiggly line, serious? Okay.
yeah,
This looking like a series circuit or a parallel circuit.
parallel.
Parallel.
Because when the current reaches junction over here, what you do? Or what do you do, guys?
Collapse.
Is split.
It would split. So let me just call this R1 and let me just call this R2. And of course, the longer terminal is the what?
Positive.
Positive.
And the shorter terminal is the
Negative.
Negative.
right. So the current will go from positive to negative like so. Until you see it splitting.
Yes.
I remember this one song, but I can't say it.
Yes, that was song it's talking about.
But I can't say that. I can't say that. Get into trouble. Anybody know the song I'm talking about?
Yes, sir.
Okay, well, once you know, I know how to sing it, right? So the current splitting in the middle. I'm gonna laugh. So if you want to, I just teach my students like an easier way to do it. Like typically in school, you would learn this. You would learn like, you would learn 1 over RT is equal to 1 all over R1 plus 1 over R2. But I don't advise students to do it like that. I just do it like this. I would just say RT is equal to open bracket 1 over R1 plus 1 all over R2 to the power negative 1. And let me explain something fast. If you do it like this, here we gotta do, right? You'd first have to add these two fractions. And then you'd have to flip it to find for RT. I say when all the time, just do this. And you get your answer. So I suppose I'll do a demonstration. Right? So this is what I advise. I advise you all to use this one. Of course, I feel like it's the easier one. It's my advice. Use this. And wait, let me just explain something. Do you all think that there could only be two components in parallel, or there could be 3 or 4 or 5, whatever?
They can have
Multiple.
multiple components.
Yeah, you could have multiple, right? You do want to have two. So you're probably wondering, so how you gonna find for RT over here? Same way. I would say 1 over R1. I would say 1 over R1 plus,
1 over R2.
and somebody else finish it from there. I'm waiting. Somebody.
1
Somebody.
over R3.
Right, 1 over R3. Close bracket to what power? So you're probably wondering where the -1 come from. The power -1 reciprocated for you one time. So like you wouldn't have to do the working like piecewise now. When you add this to find for RT, you'd have to reciprocate it. Instead of doing all that, you could do it in one shot. And you could just raise it to the power -1 and it would do the working for you one time. So to the power -1. Cool. Let's do a question now. So if you want, take a screenshot, I suppose. And let's move on to a question. Are they like the revision with the multiple choice questions?
Yes, sir.
Yes.
That it was, yeah.
Okay, cool. Don't worry, we'll do some structured questions in the next class. Alright, cool. Physics paper 1 is like guaranteed marks, eh? I'm telling you, anybody who fails physics paper 1, chances are they didn't do any work. But if you do work, guaranteed to get full marks, and this is real easy. Physics paper 1, so easy. Alright, cool. I gotta move on. Let's move on to the question now. So they're telling me that R1 is 60 ohms, and they're telling me that R2 is 40 ohms, and it was labeled 2, and it was circuit labeled 2. What kind of circuit is this?
Parallel.
It's a parallel circuit. So to add R1 and R2, I would say RT is equal to open bracket 1 over what?
R1, R2,
So those of you guys with a sharp might experience some trouble plugging this in. Right? So R1 is 60, R2 is 40. All of this in brackets to the power -1, and you should get 24, I think.
Yes, it's 24.
Right. If you have a sharp, you gotta put a bajillion brackets. Will you have a sharp or everybody here have a Casio?
Casio, so I get 24.
Yeah, watch, unplug it in and you will see you will get 24. Open bracket, fraction button, 1 over 60 plus fraction button, 1 all over 40, close bracket, x to the power, and I put -1, 24. If you have a sharp calculator, you'll have to work it like this. So open bracket, another open bracket, 1 divided by 60, close bracket, plus open bracket, 1 divided by 40, close bracket, close bracket. Then you're looking for, what's that button, boy? You're looking for this y to the x button. In your calculator, in your sharp, you'll see a y to the x button. You'll see a y to the x. You press that, and you will see this little thing come up here. And then in brackets, you're gonna put -1, close bracket, and you get 24. If you have a sharp. Just get a Casio and done. Cool. I just want to do 51 real fast. I think it's like a logical question. Remind me, guys, if you have a smaller resistor, what I mean? If the resistance is very small, what I mean about the current?
That
Okay,
the
we want to
current.
push through.
Come on, guys.
That the current would be allowed to flow through.
And if you have a really large resistor, what I mean?
It
That
will
the
not allow the current to flow through.
Exactly. So which resistor bigger, the 6 ohms or the 4 ohms?
6 ohms.
6.
Okay, where do you think more current will pass through?
The 4 ohms.
Kestrel, Amira, Adil, Vani, all you agree?
Yes, sir.
So all you understand that more current will go through the what?
R2.
R2, the smaller resistor, right?
Yes, sir.
More current will flow through the what?
Smaller resistor.
How easy this question is, eh? So if the smaller resistor is the 4 ohms and 1.8 amps is flowing through that, if you had to give me like a little inequality, right? What would the inequality for this look like? Somebody other than Zachary.
Now, what is that inequality?
Or you do that in maths, you know? Like, like x is more than 7. You do that before? Nah.
I can't remember, actually.
Okay, so if I say x is more than 7, it means that x could be what numbers?
8, 9, 10, 11,
What?
12.
Yeah, that's correct. So here what I was saying. Which one is the smaller resistor here?
4, R2.
R2. And 1.8 amps is flowing through R2. Do you think more current is flowing through R1 or less current is flowing through R1?
Less.
Therefore, the current here needs to be what? More than 1.8 or less than 1.8?
More than 1.8.
Take all the time. Take all the time. Again, more current will flow through the smaller resistor. What's the smaller resistor? R1 or R2?
R2.
So will more current flow through R1 or less current?
Less current.
So the inequality would be less than 1.8 amps. What's the only option that's less than 1.8?
1.2.
That's the answer. Yeah. All you understand? If you don't understand, tell me no. Amira, you understand?
Answer, you understand?
Zachary,
Yes, sir.
Adil, Vani, Nico. Be honest, eh? Like, I'm wondering if they actually understand. If they don't understand, tell me. Vani, I see you had on mute. I'm wondering if you're okay.
Yes, I'm good.
All right. Well, I'll call Adi. Yeah, let me know if you're all okay with the questions we did today.
Yes, sir.
Badness. Let me show you how like close we are to ending the syllabus. This is the electrical part of physics. Logic gates will come in paper too. So all we had to do now was just look at we had to look at radio nuclear physics, and that's it. Like we really close to the and like we're real close to the end. Very close to the end of the syllabus. We just have one more topic to do, which is nuclear physics. That's it. Past papers right through. Uh Anybody feel like they could tell me the answer for this one real fast? Like real fast? Tell me the potential difference across the lamp is 4. Wait, and they're asking us the potential difference across E. Now, all these resistors are in what? These resistors here are in what?
Parallel.
Parallel circuits have the same what?
Voltage.
Right, so the voltage across A would be the same as the voltage across.
B and C.
Right, so if 4 volts is across this, how much volts do you think across this?
4.
Nah, we talk about this. Look at the battery. What potential difference is the battery providing?
12.
So wait, and 4 volts is here. So how much voltage? How much volt?
Oh, 12 take away 4.
Yeah.
Okay.
So what's the answer?
The answer is B.
Yeah, that was easy. That was easy. kVl. So the next class, we're going to look at the definitions of voltage, current, resistance, Ohm's law, Joule's law. I suppose we had to go through AC and DC, but the main thing I want to do next class, I want to do some resistor questions. I want to look at V is equal to IR for sure, do some questions on that. I want to look at P is equal to VI, all of these laws, and do some past paper questions. We at the finish line, guys. We're nearly there. We are nearly there. Nearly there. Yeah. So how are you feeling so far with physics?
Pretty good.
That's good to hear.
Something like I could survive.
That is really good to hear. Happy to hear that. I will send like the work what we do today on the group chat. Or all you want me to send like all the notes we do for the whole class.
All.
Okay.
Everything, every single thing.
Okay. No problem. So guys, I'll probably have a blessed evening. See you all at 4. Might start a little later though. See now we finish a little late.
See you later.
Yeah, I will see you guys later. Like what, 4 5 p.m.?
So 5 because
Bye.
yeah.
Okay, no problem. But I'll see you guys there. Take care. Bye bye.
Yeah.
Bye, sir.